Hello and welcome to the Maths 2 component of the online BSc program on data science and programming. This video is about derivatives, tangents and linear approximation. So, in the previous videos we have seen the notions of tangents, and then we saw that it's difficult to, we wanted a way to get a handle on when tangents exist and when they don't, when they do, how to compute them and so on. And then we started, I made this comment that we need to develop some theory in order to talk about tangents in a more fundamental way, and indeed that is why we introduced the notion of limits. We talked about continuity, we talked about differentiability. Last video we saw how to compute some derivatives, and now we are familiar with limits, computing limits, derivatives, continuity and computing derivatives. So, in this video we are going to finally make the connection between derivatives and tangents, and on the way we will obtain this idea of, we will obtain this extra information about a linear approximation to a function. So, let us recall first what is differentiability. So, let f be a function defined on an open interval around a, then f is differentiable at a if limit f of a plus h minus f of a divided by h as h tends to 0 exists, and when it exists then this number, whatever that limit is called the derivative of f at a, and for each x, if we do this we will get a function that is called the derivative function. So, it is denoted either by f prime or df dx. Each notation has its advantage, by the way, and it is a classic fact that one of these is due to Newton and the other is due to Leibniz, and one made life easier as compared to the other. Okay. So, let us now recall what is a tangent. So, if you have a function f and you consider a point a which is in the domain of that function. So, a tangent to f of x at a is a line which represents the instantaneous direction in which the graph gamma f moves at the point a comma f of a, which is a point on that graph. So, you look at this graph as a curve, and then on that point we have, on that curve we have this point a comma f of a, and then we ask at that point a comma f of a what is the instantaneous direction in which the curve is moving. So, traditionally the tangent is also thought of as a line which just touches this graph gamma f at the point a comma f of a. So, we have seen examples of this. If you feel unsure of what that means, please go back and look at the examples that we did there and the pictures that we drew. Okay. So, now let us recall that when we started doing differentiability, we had this example of the instantaneous speed. That was what was the motivation for differentiability. So, this, if f denotes the trajectory of a particle, then this limit h tends to 0 f of x plus h minus f of x by h was supposed to denote the instantaneous speed. Okay. So, here meaning in the tangent we want to talk about instantaneous direction. The derivative is talking about instantaneous speed. Not so surprising, they have a connection with each other. So, let us try to exploit what that this notion of a tangent as just touching, right. So, we will express tangents as limits of secants. So, recall the notion of a tangent to the function f at a point a, that is a tangent to the graph gamma f at a comma f of a. If it exists, and this is the key point, if it exists, we can think of the tangent as a limit of secants joining a comma f of a and nearby points a plus h comma f of a plus h. Now, you may wonder what is a secant if you have been away from geometry for a while. So, a secant is a line which is obtained by joining 2 points of a curve. So, in this case you have your graph, you take 2 points on the graph and you join them, and that is a secant. So, here the suggestion is that you take the point a comma f of a and a nearby point a plus h comma f of a plus a h, and you join these 2 points, and the line that you get is a secant, and then you allow your h to come closer and closer to 0. So, your secant will slowly it is hoped move to the tangent. So, if this is not apparent, let us see an example of this. So, let us maybe look at this animation that I have here. Okay, so what is this animation doing? So, let's stop this for a second. Okay, let's begin from here. Okay, so here's your point B, which is the point 0 comma 0. So, here's point 0 comma 0. So, here your a is equal to 0 and f of 0 is 0. That is because we are plotting the sine function. So, f of x is sine x. So, sine of 0 is 0, and here is a point close by. So, I have started this from the point 2 comma 0.91. So, the point capital A is your point a plus h comma f of a plus h. So, a plus h here is 2, and sine of 2 is whatever it is 0.91, and now we are going to vary h, right, and we are going to bring it closer and closer to 0. So, this point will come along the function, that is a graph of the function. It will come closer and closer to this point B, and this red line is the secant, that is the line joining B and A, and let us look at what happens to the secant. And this black line, which I have called unfortunately labeled as H, is the tangent to f at the point 0. So, that is what this is. So, let us play the animation now and see what happens. As you can see, it is coming closer and closer and closer and closer, and as the point comes further close, it is very close now, and yeah, as it approaches B, it becomes the tangent, right. So, this is the idea of that the tangent is a limit of secants. Yeah. So, this is not a formal statement, that one can make it formal, but we will utilize this statement. Let us just just to get an idea, let us look at another example, maybe the example of x squared. So, here is the graph of x squared. Okay, so once again we have these points. This time I have not plotted the points. Let me stop this. Okay, so this is at 0.5. So, we are looking at the tangent at 0.5. So, if the green curve is f of x is x squared at the point 0.5 comma f of that, which is 0.25, because it is x squared. So, the function is x squared. So, 0.5 squared is x squared. So, this is the point 0.5 comma 0.25, and we are joining this point with neighboring points. We are drawing the secant, which is the red line, and the black line is the tangent. Yeah. So, if we hover here, it says tangent to f at x is equal to 0.5 comma. So, x is 0.5. Okay, and let us play it now. So, if we play it now, you can clearly see that as this point comes closer and closer and closer, the red line, which is the secant, comes closer and closer to the tangent, right. So, and just to show that it can come in a slightly strange way, let us look at another example, which is the example of x cubed. So, let us look at x cubed. So, once again the green curve is f of x is x cubed, the red line is the secant, and the black line is the tangent, and yeah. So, this is a line joining this point b comma f of b and b minus a comma f of b minus a, which is this point a over here. Okay. So keep an eye on this red line. Let's play this and see what happens. So as you play it, this red line comes closer, it actually goes over and then it starts moving back. Yeah, and now again it's moving back, and now as A is coming to B, it becomes the tangent. Okay. So you could have this behavior depends on how close you are, right. So in this case it's crossed over, but then it's again coming close by. So really if we had chosen something very close to this point B, it would have come closer and closer and closer automatically. But if your points are far away, it may first go away and then come back, right. But that's allowed when you do limits, because when you do limits, the idea is that eventually it comes closer and closer, right. So that's what we are seeing here. Okay. So I hope you have gotten the idea of that was expressed in this slide, namely that you can think of a tangent as the limit of secants. So if it exists, we can think of the tangent as a limit of secants joining a comma f of a and nearby points a plus h comma f of a plus h. Okay. So let's write down what is the equation of the secant, right, which joins these two points. So we have done the in Maths 1 you must have studied how to write down the equation of a line which passes through 2 points. So the equation of this line is going to be y minus. So first, what is the slope? So y minus f of a is equal to slope times. So what is the slope? So in this case, the slope is f of a plus h minus f of a divided by a plus h minus a. This should ring a bell, times x minus a. So this is the equation of the secant. Let's just cross check that this is indeed the correct equation. So if you put y is equal to x is equal to a and y is equal to f of a, then indeed both sides are 0. So this passes through a comma f of a, and if you put x is equal to a plus h and y is equal to f of a plus h, then the right hand side, well, I should have written the right hand side one more step here, f of a plus h minus f of a divided by h times x minus a, right. The denominator becomes h. So this expression is familiar, f of a plus h minus f of a, right. And if you substitute x is a plus h and y is f of a plus h, indeed it is satisfied. So it passes through both points. So in case you have forgotten the equation of a line passing through 2 points, I have anyway checked that it passes through these 2 points. Okay. So this is the equation of the secant that is given above, and now what we are going to try and do is ask what is the limit of this. So what happens in the limit to this equation. So let's make that precise. So let f be a function differentiable at the point a, and then the tangent to f at a exists and is given by y is f prime a times x minus a plus f of a. Yeah, that expression in the previous slide, let's just look at that again. This is the expression, y minus f of a is f of a plus h minus f of a divided by h. So this expression here in the limit becomes f prime a, and then the rest is exactly what we had. So y is f prime a times x minus a plus f of a, right. And so this is saying that if the function is differentiable, which means that in the limit, that expression that we had that has a limit, and that limit is we have called it f prime a, then the tangent exists and is given by this equation. And on the other side, if the tangent to f at a exists and it is not vertical, so that is it is not the line x is equal to a, then f is differentiable at a, and the equation of the tangent is the same as above. Once it's differentiable at A, it's forced that it's this. How did we get this? Well, let's write down the equation that we had, expression that we had in the previous slide. So, if I take the f of A on the other side, we had y is f prime A times, y is f of A plus h minus f of A divided by h times x minus A plus f of A. This was the expression. Now, in the limit, meaning as limit as h tends to 0, if this limit exists, which is exactly saying that the function is differentiable, then of course, in the limit you will get the expression above, right. If this limit exists, so if f is differentiable at A, then this expression here, the limit is exactly what we have here, right. This is the limit. Then the limit of this thing in the red box is f prime A, which is in the orange box, and that is how you get this expression. Okay. So, I have more or less given you a proof, well, not exactly, but at least given you a fairly good holding point for the statement, why the statement holds. So, I will just repeat the statement. If the function is differentiable at the point A, then the tangent to f at A exists, and it is given by this expression here, y is f prime A times x minus A plus f of A. And what is this saying? The other statement, it is saying more or less the converse. Suppose the tangent exists and it is not vertical. Okay. So, let us in a minute we will study why we have this caveat. So, vertical meaning it is not like this, right. There is nothing preventing the tangent from being like this, after all. Yeah. So, if that is not the case, then f is differentiable at A, and the equation of the tangent is y is f prime A times x minus A plus f of A. So, in other words, what we are saying is that differentiability is equivalent to the tangent existing and being given by this expression, except in the case where you have a vertical tangent. Yeah, that vertical tangent is not captured by the definition of derivative that we have made. We can actually modify that definition if we allow something called infinity, then we will also be able to deal with vertical lines, but for now that is not what we are doing. Okay. So, let us talk about this getting the tangents. So, let us compute the equation of the tangent line for these examples. So, we have seen these examples before, right. So, we know what are the derivatives. So, the tangent line here, we want to find it at the point A is 0. So, f prime x is 15 x squared minus 34 x plus pi. So, that means f prime at A, which is 0. So, f prime at 0 is pi. So, therefore, the equation of the tangent at A, tangent to f at A, so A is 0. So, at 0 is y is equal to f prime at 0, which is pi times x minus 0 plus f of 0. Okay. And what is f of 0? F of 0 is minus 0.5. So, this is pi times x minus 0.5. This is the equation of the tangent line to f at 0. Okay. Let us do this second example. So, f prime x here is minus sine of x. So, we want to evaluate this at pi by 3, which is the point we are given. So, f prime of pi by 3 is so that is minus sine of pi by 3. So, I suppose minus pi by 3 is root 3 by 2, sorry, minus root 3 by 2, and so therefore the equation of the tangent 2f at A is y is equal to minus root 3 by 2 times x minus pi by 3 plus f of pi by 3. What is f of pi by 3? So, cosine of pi by 3. Okay, so cosine of 60, if I remember right, is half. So, this is minus root 3 by 2 x minus pi by 3 plus half. That is the equation of your tangent line. And let us do this final example. This will give us some. So, here let us find out f prime x. But what is f prime x here? This looks like a complicated function. But last time we have studied the product rule for functions, right. So, if it is a product of two functions for which we know how to find the derivative at a point, we can do it for by the product rule. So, by the product rule, this is 1 times tangent of x plus x times derivative of tangent of x, which is secant squared x. So, this is tan x plus x secant squared of x. Okay. So, now I want to do evaluate this at the point pi by 4. So, at pi by 4, so that is 45 degrees. So, that is tangent of pi by 4, which if I remember right is 1, and then the rest secant squared of pi by 4. So, I think so cosine of pi by 4 was 1 by root 2. So, secant of pi by 4 is root 2. So, secant squared is 2. So, this is going to be 1 plus pi by 4 times 2. So, this is 1 plus pi by 2, and now so therefore, the equation of the tangent line is y is equal to 1 plus pi over 2 x minus pi by 4 plus f of pi by 4. So, which is pi by 4 times tan pi by 4, which we just saw was 1. So, this is just pi by 4, and I guess we can't simplify this much more beyond this. So, this is what it is. Okay. So, this is the tangent line to this function x times tan x at pi by 4. So, I hope you can see that computing the tangent is the derivative is useful, because now I can actually get the equation of the tangent line. Yeah, this is something you can plot in a graph. So, I hope you understand how to compute the equation of the tangent line once we know how to compute derivatives. Fine. So, let us look at this example. F of x is x to the power 1 by 3. So, for this example, let us go back to our animations. So, here is x to the power 1 by 3. Let me bring this into the middle. Okay. So, here the green curve here is the graph of the function. So, this function is x to the power 1/3. The red line here is the secant. So, that is the line joining B, which is the point 0 0, and the point A, which is going to move towards B. And where is the tangent? Well, here is the tangent. Yeah, the tangent is the y axis in this case, and this is the vertical tangent. And why is this the tangent? Well, you can see that as you come close, as the graph comes close, indeed the instantaneous direction of this graph at the point 0 0 is indeed vertical, right. So, this is the tangent. Okay. But what happens now? Once you play this, let us look at what happens to the secant. So, the secant comes close, and indeed it approximates the tangent, right. So, the secant approximating the tangent is not really a problem here. Okay. So, why is this a big deal? why I am making a big deal about this example. So, let us try to compute what happens to the derivative. We have seen that if you have x to the power a, then the derivative of this function I claimed was a times x to the power a minus 1, right. And I made some small remarks about what happens if a or a minus 1 is negative. In that case, we have a problem at 0, and really that is exactly what happens here. So, for x to the power 1/3, if you have a point for if x is not 0, f prime of x, where here f prime means f of x is x to the power 1/3, then f prime of x is 1/3 times x to the power 1/3 minus 1, which is 1/3 times x to the power minus 2/3, or in other words 1 over 3 to the power x to the power 2/3. So, you square x and take its cube root. That is what the function f prime is, if x is not 0. But at 0 you can see there is a problem. So, you have x in the denominator, and that is exactly what happens. So, if we try to compute this limit at 0, let us see what that gives us. So, limit h tends to 0, f of 0 plus h. So, this is f of h. So, this is h to the power 1/3 minus 0 by h. So, this limit h tends to 0, h to the power 1/3 by h, which is limit h tends to 0, 1 over h to the power 2/3, and this limit does not exist, or yeah. So again it depends on what, how the convention is. So, one way of thinking of this is that we have this number called infinity, and if we allow infinity, then really we can salvage the situation. But since we are not doing that, we will say this diverges to infinity, right. And because that is the case, we say this. So, therefore, it does not exist. So, therefore, this limit in our notation we say it does not exist. Okay. So, this function is not differentiable at 0. And what is the issue? The issue is that we get y is equal to or rather x is equal to 0 as the derivative, sorry, as the tangent. And the problem is, if we write the form y is equal to mx plus c, this works only for lines which are not vertical. So, for the vertical line you have to separately say x is 0, right. So, the problem is your m is only a real number. So, if you allow m to be infinity, you can sort of divide by m, and that will give you a 1 by m. So, 1 by infinity, which is 0. So, you will get x is equal to 0. Okay. And if you allow that, then indeed we can salvage the situation. So, that is what the problem is. So, that is why in the previous slide we had to make this caveat about the tangent not being vertical. Okay. Fine. So, let us now consider the notion of linear approximation. So, what is linear approximation? So, we have a function f and we want to approximate it by a linear function. So, what is a linear function? So, let us recall that a linear function is a function of the form L of x is c plus d times x. Yeah. So, we have seen this kind of thing before in our linear algebra videos, if you have seen them before. L of x is f of a plus m times x minus a. Okay. Again, with the caveat that if you allow vertical functions, vertical linear functions, then that function will just be the function x is equal to a, point form for a line. So, if you have L of x is f of a plus m times x minus a, then m is the slope. And how do I know that this is the linear function which takes the value f of a at a? Because if you put x is equal to a, then indeed on the right hand side you get f of a. So, L of a is equal to f of a. So, it will pass through the point a comma f of a. So, that means the graph of the function L will at the point A will be the same as the graph of the function f at the point A. Okay. So, we want to choose a linear function which best approximates the function f of x around the point A. Okay. So, that is f of x is approximately equal to L of x for all x close to A. And you can see that I have written this best approximates in italics. So, really the point is here we want to get a hand on what it means for best approximates. Unfortunately, this is a slightly technical notion, somewhat difficult to explain, but what really we are saying is the following: amongst all possible linear functions, which linear function approximates this best, in the sense that if you have some other approximation, then the difference between f x and L x will be smaller as compared to the difference between f x and that other approximation for all x which are close to A. So, there is some small interval for which that the difference of f x and L x must be smaller than the difference of f x and any other linear function, right. This, so, in this sense it is best approximates. Okay. So, there are many issues here. I mean, first of all, why do we even know that such a thing exists? So, turns out that if f is differentiable at A, then the best linear approximation is in fact given by the expression for the tangent. So, L of x is f of a plus f prime a times x minus a. Conversely, if there is a best linear approximation for f at A, then f is differentiable at A, and once we know it is differentiable at A, the best linear approximation must be of this form, f of a plus f prime a times x minus a. Okay. So, this is not very difficult to imagine. It is a very intuitive statement, because if you looked at the pictures that we had, indeed as the function came closer to the point A, as x came closer to the point A, the function value came, the graph of the function f was very closely approximated by the tangent. So, for example, in this video here, when we play this, right, as the function is coming closer, you can see the graph is, yeah, it's very, the tangent line is very close to the graph, right. So, this blue line is very close to the green line, sorry, the green curve at the point 0 0. In fact, here it is almost indistinguishable. Yeah, even in the other examples, let's look at one more example, maybe the example of x cube. You can see here, you can stop the animation. Yeah, you can see here at the point, this is at the point 0.5. We don't need the red line. Close to this point, the curve, meaning the graph of the function, and the tangent, they are very, very, very close. Okay. So, that's the intuition behind the best linear approximation, and this is the statement that indeed it is the best linear approximation. Unfortunately, we can't prove it in this series of lectures, but those of you who are more mathematically inclined can give it a shot by using the definition of the tangent. Okay. So, let us do these examples. F of x is x cube, A is 1. What is the best linear approximation? This is exactly the same as finding the tangent. So, here you will have to find f prime at 1. So, f prime at 1 is 3 times 1 squared. I am doing it faster now than I did earlier. So, the best linear approximation is L of x is f prime at 1, which is 3 times x minus 1 plus f of 1, which is 1. So, this is 3x minus 3 plus 1. So, 3x minus 2. Okay. So, if you have secant, you want f prime, so at 0. So, f prime at 0 is, so the derivative of the secant of x is tangent of x times secant of x. So, this is tan of 0 secant of 0, tan of 0 is 0. So, this is 0, and that tells us that y is equal to, so L of not y, but L of x, the best linear approximation is 0 plus 0 times x minus 0 plus f of 0. So, secant of 0, and what is secant of 0? Secant of 0 is 1. So, at 0 the best linear approximation is the constant function 1. Okay. So, this is a very interesting situation when the best linear approximation is a constant function, or in other words the tangent is flat. Yeah. So, we will be studying this phenomenon in the next video, and we will be picking up things called turning points. Yeah, this was something you may have you can recall from Maths 1, and this phenomenon will be explored in more detail in the next video. So, let us just recall what we did in this video. We have finally been able to link up the tangent with the derivative, namely the tangent has an equation which is given by f prime of a times x minus a plus f of a, and it turns out that expression is also the best linear approximation to your function f. Thank you.